Alright, I'm going to start with Josh's question first. What is something that, if lost forever, I would be the most upset by that? And I really resonate with what Josh said because my computer also contains the vast majority of my life's work. I have personal projects that I still work on from time to time that I would be absolutely devastated to lose. And I have some projects that I have absolutely no intention of ever working on again, but I still need them because they're providing a knowledge base on how to do certain things that are not necessarily easy to find using Google. Shocking, I know. Now, I do create backups periodically, but I keep my backups in my apartment, which is also where my computer is. So the backups might help in the case of a hard drive failure or if it gets stolen, but it's entirely possible that I could lose both the backups and my computer in, say, a fire. The only other item that I own that I feel even remotely emotionally tied to are some of my t shirts. I tend to buy shirts that are unique. Many of them would be very difficult to replace. They were either limited edition, such as the shirt that I got from funding a video game's Kickstarter campaign. And then there's my favorite shirt, the one that features Obama and Kim Jong un hugging. This again isn't a shirt that I purchased in any chain clothing store and I can just order another one. This shirt came out of a tiny hole in the wall shop somewhere in China. I wouldn't even know where to begin looking for a replacement. But unfortunately, some of these shirts aren't going to last too much longer. They've already started getting holes, and eventually I'm going to have to make the call that I can't wear them anymore. I only hope that when that day does come, I'll have found something equally fun and unique to wear instead. Now, for the other question, what's something that seems really complex but actually isn't? And for this, I'm going to explain how machine learning works. For the less mathematically inclined among us, don't worry, I'm not going to do anything more complicated than simple algebra. So let's get into it. Suppose you have a graph, just like this. Maybe the x-axis is something like your high school GPA, and the x-axis is something like your current salary. Now this graph is going to be populated with data, perhaps looking something like this. Each data point represents a single person with a corresponding GPA and salary. The purpose of a system like this is to take a student, somebody who doesn't have a salary yet, and try to predict what their salary will be by only looking at their GPA. This model will be a line. In fact, it's typically called the line of best fit and will probably look something like this. To predict what a student's salary will be, we simply look at this line and see what the associated salary is for a given GPA. And so that's the main idea behind this model. Now, how do we find this line? Well, you'll remember from your high school algebra, I'm sure, that the formula for a line is y equals mx plus b. The m represents the slope of the line, and the b represents the y-intercept. So all we need is to find a slope and a y-intercept that gives us a good line. Which brings us to the question, what makes a line good? Why did I draw this line like this and not something like this? Or maybe like this? We need some way to determine how accurate or how close to the data a line is. And when I say how close to the data, I mean it in a literal sense, because that's going to be how we determine the goodness of a line. How far is the line from a given data point? We can measure the distance from the line to the data point and call that the goodness or the closeness of the line. But instead, we're going to take the square of each of those distances. And there are good reasons to do this, to use the square instead of just using the distance as it is. But I'm not going to really get into what those reasons are, so you'll just have to trust me on this one. Note that I changed our line equation slightly to fit the notation better. Y prime is representing the y-coordinate of our line, whereas y is the y-coordinate of our data point. And the distance between the line and the data point is therefore y prime minus y. So the closeness of this line is calculated using the square of the distance from the line to a data point. But we have lots of data points, and we're more interested in closeness to all points, not just a single point. So the closeness is going to be determined by the sum of the squares. Remember that equation we had for our line? We're going to substitute that equation in for our y prime. So our closeness equation now looks like this. Now the goal of our model is to get this line as close to the data points as possible. And the way to do this is to take the derivative and set it equal to 0. These equations will look like this. But I promised you no advanced mathematics, so I'm not going to do the full derivation of these equations. I'm going to just skip ahead and tell you that these equations will end up looking like this. Each x represents the x-coordinate of a data point, each y represents the y-coordinate of a data point, and n is the number of data points. By putting these values into our equations, we can find the slope and the y-intercept that give us the line that most closely fit our data, giving us the so-called line of best fit. And that's it. That's basic machine learning. This particular model is called linear regression. Okay, so there's obviously a lot more to machine learning than this. You remember these equations? Even for linear regression, we don't really do it this way. Instead, we usually use matrices for our x values, our inputs. And so here you can see the same linear model in a matrix form. And by doing it with matrices instead, it helps us because we can solve for many unknown variables at the same time. So for example, instead of a linear equation, we could do a quadratic equation and fit for 3 unknowns. And this final equation seen here, beta equals x transpose x inverse times x transpose y, this is a very famous equation in machine learning, and it has lots of applications. But even that is still just putting lines on a graph. How does this relate to, say, self-driving cars? Well, it doesn't really. Neural networks are an entirely different kind of machine learning, and one that unfortunately requires much more mathematical expertise to understand. So I feel it unwise to try to explain that particular model at this time. But now that you know linear regression, you know your first machine learning technique.